Hello everyone, welcome to the chemistry channel. So today we're going to be talking about the wave behavior of matter, and this will be our fourth lecture of atomic structure. So today we're going to be talking about two different topics. The first one is the de Broglie wavelength, and then the second one is the uncertainty principle proposed by Heisenberg. So then we're going to conclude with two practice questions. So with that, let us begin. So the first thing that I want to note is that light has been shown to have both wave and particle-like qualities. So wave can be described as both a wave and a particle. And this physicist named Louis de Broy, for his PhD thesis, actually extended this idea to matter. So he extended the idea of light having both wave and particle-like qualities to matter itself. So therefore, de Broy stated that moving matter, so it has to be moving, can behave as a wave, or in other words, it can be described as a wave. So therefore, he derived an equation in order to relate both the mass of an object and its wavelength. So he derived an equation in order to relate both the mass of a moving object and wavelength. And we're actually going to derive this equation together. It's very simple to do. So we start off with E is equal to HF, which we showed in our one of our last videos. And we know that frequency is equal to C over lambda. So therefore we can substitute this in here saying E is equal to HC over lambda. And you may remember or may know of a famous equation, E is equal to mc squared. This is mc squared is equal to energy, so therefore we can set these two equations equal to each other. So therefore mc squared is equal to hc over lambda. However, particles with mass cannot move at the speed of light. So therefore, instead of saying c, we substitute in v for velocity. So mv squared is equal to hv over lambda. So then we can divide v from both sides, giving us mv is equal to h over lambda. And then when we solve for lambda, we get mv lambda is equal to h. So then we keep lambda alone on this side by dividing mv. And this gives us the equation lambda is equal to h over mv. And this is the de Broglie wavelength equation. So m is equal to the mass of something in kilograms. V is equal to the speed of something in meters per second. And h is equal to 6.626 times 10 to the negative 34 joule seconds. So that's just Planck's constant. So those of you in physics can probably simplify this equation to simpler form. And you'll notice here that the denominator is m mass times the speed. And you may know, if you're in physics, that this denominator is actually equal to the momentum. So momentum. So instead of saying mv, we can say that lambda, or the wavelength, so lambda, the wavelength, so let's actually put that up here too. So this is the wavelength, and it's in meters. So that means meters. So lambda, the wavelength, is equal to Planck's constant divided by p, which is the momentum. So therefore, after deriving this equation, we can come up with this relationship. As p increases, or the momentum increases, the wavelength decreases. And this should make sense because momentum is directly related to v, and velocity is directly related to energy. So therefore, as our velocity increases, our momentum increases. And as our velocity increases, our energy increases, and as our energy increases, the wavelength decreases and the frequency increases. So this should actually make a lot of sense to you. So what does this equation tell us? This tells us that any moving matter, therefore any moving piece of matter can form or be described as a wave. So therefore we can extend this to electrons. This means that moving electrons, so this means electrons can also form a wave. So now that we have this idea, which is a very important idea, this idea will be very important in the next video, that moving electrons can be described as a wave. This idea caused a lot of questioning to occur in the physics community. And it actually brought about the uncertainty principle, which we will talk about after discussing these questions that appeared within the physicists' heads. So let's talk about the first question. So imagine a baseball falling towards the earth. And those of you in physics should know this very well, that classical physics can accurately define both the momentum of the ball and the velocity of the ball and the position of the ball all simultaneously and very accurately. So classical physics can simultaneously and accurately determine the position and momentum of macroscopic objects, so objects that we can see. So classical physics can simultaneously and accurately, so that's important, simultaneously and accurately determine the position and momentum of a macroscopic object. However, this is not the case for microscopic objects, in particular subatomic particles. So we cannot measure and determine the position and momentum of a moving object accurately when it's at the subatomic level. So therefore, we cannot do the same for subatomic particles. However, why? Why can't we do this? Well, it is because as the size of a moving object decreases, its behavior can increasingly be described as a wave. And subatomic particles, including electrons, are all very, very, very small species. So therefore, their behavior can be described almost perfectly as a wave. And when you can describe something perfectly as a wave, things start to get weird. And that's what we're going to go into in a little bit. But first of all, I want to define what the uncertainty principle is. So the Heisenberg uncertainty principle states that it is impossible to simultaneously know the exact momentum and the exact position of a moving object. So the Heisenberg uncertainty principle is described by this equation here. So delta x times delta p is greater than or equal to h over 4 pi. So what do all these variables mean? Well, delta x is the uncertainty associated with the position of the object. Delta p is the uncertainty associated with the momentum, and h is the Planck's constant. So h is Planck's constant. So that is what all the variables are in the Heisenberg uncertainty principle. So why is there this uncertainty with waves? Well, I am going to give you a very, very rudimentary explanation of this. Now, this explanation is probably not going to be required for you to understand in order to do well in your general chemistry classes. However, I find that it is helpful in order to understand why you have this uncertainty in the first place. So the thing that I want you to do is imagine you have this sine wave here. And as you can see here, this sine wave is really large. So the first thing I want you to note is the wavelength of the sine wave here. So the wavelength, if we measure it from peak to peak all across, we can see that the wavelength is constant. So the wavelength is constant. So this wavelength is constant. Now, what's the relevance of this wavelength being constant? Well, the relevance of this wavelength being constant is that it allows us. So actually, let's rewrite this. Let's be more specific here. So the constant wavelength allows us to precisely measure the momentum. However, why would having a constant wavelength allow us to precisely measure the momentum? Well, it's actually because the momentum, if we look back at our de Broglie relationship, lambda is equal to h over p. Therefore, when we solve for p, p is equal to h over lambda. So therefore, if we have a constant value for lambda, the momentum can be precisely measured. However, we cannot precisely measure the position. Why? Well, you'll see in the next video that that all waves can be described by a wave function, and when we square the wave function, we get the probability. We get a probability distribution. So this distribution tells us the possible areas in which an electron could occupy. So if we squared this whole wave right here, the space in which the electron could occupy is huge. So therefore, we cannot precisely measure the position of a moving species when we can precisely measure the momentum. So what if we could confine? So what if we did the opposite? What if we could confine an electron to a certain space? So in order to do this, you can add a bunch of different wave functions together, and they add together to form this pulse wave. So as you can see here, the space in which the electron can be occupied in, so the space in which the electron can occupy is much smaller, so the uncertainty is much smaller. However, if you notice here, the wavelength cannot be measured that accurately, and you can see this because it doesn't look too much like your normal wave. So in order to find the wavelength, we take the average wavelength, which is not as precise. Therefore, when we increase the precision in our position measurement, we decrease the position in our momentum measurement. So the thing that you do have to know is that we cannot simultaneously exactly measure both the momentum and the position. So that's what you do have to gather from all this. And you also have to gather from all this the relationship between the uncertainty in position and the uncertainty in momentum. As the uncertainty in position increases, the uncertainty in momentum decreases. And as the uncertainty in position decreases, the uncertainty in momentum increases. So that is something you do have to know, and this relationship you have to know. However, this whole explanation here is probably something that is out of scope for the class that you are taking. So now that we know how all the theory behind it, let's do some practice questions. So this is going to end off our video today. So what I want you to do is I encourage you to try these practice problems for yourself and come back and check in with me in a little bit. So I hope that you did these practice problems. So let's do these together. So the first thing we have to do is convert these different values to SI units. So this 10 grams is not in SI units. We have to convert this to kilograms. So 10 grams is equal to 1.00 times 10 to the negative 2 kilograms. So now we can actually solve for the wavelength. So the wavelength we can find with the de Broy equation. So wavelength is equal to h over m times v. And now we can just do a plug and chug. So h is Planck's constant, which is 6.626 times 10 to the negative 34 joules per second. And then the mass is 1.00 times 10 to the negative 2 kilograms. And then our speed is 40 meters per second. Now make sure that you have the correct number of sig figs. We have 2 here, 3, 3. So our measurement should have 2. So therefore our wavelength will be approximately equal to around 1.5 times 10 to the negative 19th meters. So now let's do the second problem. Here I ask you to find the uncertainty associated with its position. So this is begging for you to use the Heisenberg uncertainty on principle, which is the uncertainty associated with the position times the uncertainty associated with the momentum, which is greater than or equal to h, which is Planck's constant, over 4 pi. So in order to find the uncertainty associated with the position, you just have to solve for that variable. So delta x is equal to h over 4 pi times delta p. Now delta p, we can solve for it together. So delta p is the uncertainty associated with the momentum. So all you have to do is multiply the uncertainty of the speed times the uncertainty, multiply the uncertainty of the speed times the momentum. So we would write this as the change in p is equal to 0.030 times 6.0 times 10 to the 5th meters per second times the mass, which is 2.0 times 10 to the negative 20th kilograms. So now when we plug all of this in, so you plug this in here, and then this is your Planck's constant, so you have 6.626 times 10 to the negative 34 joule seconds. So let's just make sure we have the appropriate number of sig figs. So here you have 2, here you have 2, here you have 2, and here you have 3. So therefore, your overall measurement should have 2. And when you plug this in your calculator, you will get the uncertainty in the position is greater than or equal to 1.5 times 10 to the negative 19th meters. And I actually change this to greater than or equal to as well, just so I don't confuse you. Sorry about that. So let's change that. Okay. All right, so that's how you solve that problem. So that is how we determine the Heisenberg uncertainty principle, and that is the de Broglie wavelength. So this was a relatively short video. In the next video, we're actually going to start getting into atomic structure. So we're actually going to start getting into the applications of all the previous videos. So that's a very exciting section. So I thank you all for watching. I hope this helped you understand something or cleared something up for you. And if you have any questions, put them in the comments section. I thank you for watching and see you next time. Good luck.